My invisible friends, hello and welcome back to our series on electrical engineering. Tonight, we start a very short series of 4 videos dedicated to the electronic valve, the diode. The first of the videos, this one, is about the best possible diode there could be, the ideal diode. This video will be the foundation for the other 3, so let's pay attention to what we say here. The second video will be about the real diode, and the third one on the rectifying circuits. The last one of the 4 videos is about a very special type of diode, the Zener diode. Now, without further ado, let's begin. The name diode is an anachronism. Let's see, engineers have been wanting to have an electronic valve for some while. It was a device that would let current flow in one direction, but which would block current that tries to flow backwards. And it was in 1904 that Sir John Fleming came up with this idea where he used a vacuum tube with 2 electrodes in it and created the first electronic valve. Because that electronic valve had 2 electrodes, the name was diode, electrode, diode. Nowadays, diodes are solid state, so in all property, they're not diodes. They are solid state rectifying devices or solid state valves or electronic valves, whatever you want, but the name stuck and we continue to call them diodes to this date.
Engineers have been observing the performance of valves in hydraulic circuits for many years and desiring having such a device in electric circuits. A valve in a hydraulic circuit is a device that prevents liquid from backflowing. A valve in a pipe will let liquid flow in one direction only, but will block the liquid if it tries to backflow, like the valves in the heart, being the real ones or these artificial ones on the right. Even in the vein, we have valves that let blood flow in one direction, but if the blood tries to backflow, those valves will shut down the flow of blood. An electric valve is a desire, it is a wish. We want a device that lets current flow in one direction only, but blocks current that tries to backflow. It is called a diode for historical reasons, as I've said before. What does it look like? What symbol we use to represent that in circuit diagrams, in schematics? What are the polarities for voltage and currents in a diode? And very importantly, how does it behave? What is the relationship between voltage and current in the ideal diode? Here's a picture of the rectifying diode that you will use more often in this course. It is in your toolkit. There you identify with a silver band the so-called cathode of the diode. Yes, the 2 terminals of the diode are not interchangeable. One is the A terminal, the other is the C terminal, also labeled as the K terminal. One is the anode, the other is the cathode, which also are names that make reference to the original vacuum tube, but we continue to use them. Well, you see, in a diode, the current will flow from A to C, but not backwards. We represent the diode with a symbol that looks like an arrow between the anode and the cathode. The positive direction for the current in a diode, of course, is from anode to cathode. The positive polarity of the voltage signifies that the anode is higher than the cathode. VD tells us how much higher than the cathode the anode is, VA minus VC. Well, it's a non-symmetrical device. A and C are not interchangeable when you connect them in a circuit, of course. We're used to ideal elements like the resistor, the inductor, and the capacitor being described, their behavior, by a single equation. V is I for the resistor, V is L di dt for the inductor, V or I C dV dt for the capacitor. Not so for the diode. You see, the diode is a nonlinear device, so its behavior, V versus I, is described not by one but by 2 different equations, this way. If the current is positive, the current is flowing from A to C, then the diode behaves like a closed switch. Its voltage across will be zero. It's represented like a closed switch, like a short circuit. But if the voltage is negative, so that is, if we try to apply voltages so that the cathode is higher in an attempt to get a current flow backwards through the diode will have none of that. It will open up, the current will be zero, and it will behave like an open circuit, like an open circuit, like an open switch. There are two equations that describe the diode when it's open or when it's closed, when it's conducting or when it's not conducting. It is either an open circuit or a short circuit. Which one will that be? Those are pictures of very old types of vacuum diodes. Observe that I've used the adjectives open or closed diodes. What do I mean by that? In electrical technology, open and closed are used backwards with respect to the way we use those adjectives in the real world. When a door is open, people can go through it. When a door is closed, people cannot go through it. But in electricity, a switch like this one, the so-called knife switch, where you tie up a cable to the screw on the left, and then you tie up another cable on the screw on the right. When that switch is open like that, current cannot flow. It's an open circuit. But when you lower the lever, you close the switch and the current may flow through. Well, you see, we use open and closed when it comes to electricity the same way as we do for that switch. We say, in a diode, when it's conducting, we think of it as of a closed switch, and we say the diode is closed, as if it were a closed switch. It behaves like a wire, like a short circuit, because it's ideal 0 volts. But if the diode is not conducting, we say that it's open, like an open switch. It behaves like an open circuit. There are no amperes flowing through that. It's an ideal diode. An alternative way of describing the behavior or the state of the diode is saying the diode is on when it's conducting, or the diode is off when it's not conducting, or even say the diode is in state 1 when it's conducting, or 0 when it's not, or vice versa, depending on the convention that you are using. That's the point. Let's represent the behavior of the diode graphically. We take two axes, a vertical one for the current in the diode, a horizontal one for the voltage in the diode. This segment of line there represents when current is positive, the voltage is 0. That represents the diode when it's conducting, when it's on, when it's in state 1. And this other one, that represents the diode when the voltage is negative, the current is 0. That represents the open diode when it's off, when it's in state 0. So that is the characteristic of the ideal diode. That is what we want to achieve. Tutorial time. Let's take a circuit that has one source, 15 volts from the top to the bottom of the circuit, 4 resistor, and one ideal diode. How do we solve the circuit? Well, depending on whether the diode is on or off, the diode will be represented by a short circuit or an open circuit. Look, if that diode is on, it's closed, then that is your equivalent circuit. If, on the contrary, the diode is off, it's not conducting, then the actual circuit looks like this one. How do we know which one to use? We don't. Then we assume one, we solve it, and check if the condition is met. Let's see, better with an example. Let me assume the diode is off and is represented with an open circuit. And then we'll solve the circuit, find the voltage in the diode, which is VA minus VC, the anode voltage minus the cathode voltage, and verify that that voltage is negative, because if that's negative, it is true that the diode is open, it's off, it's in state 0, and that circuit is correct. That is what I'll do. Well, sure, that is the voltage I need to compute. Identify the nodes, reference node, anode, and cathode, the branch currents as usual, and write a K-scale equation for node A and for node C, and we solve for VA and VC, and the voltage in the diode is VA minus VC, which happens to be a positive number, and that contradicts the assumption that the diode was closed. So you say, bummer, VD is not negative. So I was wrong when I assumed that the diode was open. Bummer, I need to recalculate the circuit now with a closed diode. And that is exactly what I'm about to do. Look, the circuit with a closed diode. After we solve the circuit, we will compute that current, this current, and verify that it's positive flowing from A to C. That is a condition, and then we will know that we were right in that the diode is closed and the currents and voltages in that circuit will be the correct ones. Let's proceed. That shorted diode there will join those two junctions into a single node 1, the branch currents, and there is only one K-scale equation for that node 1. We solve for V1, and once we have V1, of course, you can compute the current IA, the current IB, and with IA and IB applying K-scale to this little Gauss surface, you can say the diode current is IA minus IB, like so, and compute the current ID and verify this time that that 0.56 milliamps is truly a positive current, so the diode is truly conducting and this circuit is true, and the values of voltages and currents I compute in it will represent the behavior of the circuit, assuming that the diode is truly ideal. If we have more than one diode, let's say we have two diodes, in that case we have four possibilities. Both are off. The first one is off and the second one is on, or vice versa, or both diodes are on at the same time. So we have four different circuits to solve and verify all the conditions to make sure that which one of the four configurations is the correct one. How many possibilities? 2 to the 2. But if we have three diodes, then we have 2 to the 3 possibilities, right? Like so. In general, if we have n diodes, we will have 2 to the n different combinations. It can be really bothersome, right? Laborious to analyze a circuit with ideal diodes this way until we hit the one configuration where all the conditions are met for each one of the diodes. What of an exam? In an exam, I would give you the circuit with the three diodes, for instance, and tell you, prove whether the connection 101 is true or false. There. And you just draw the equivalent circuit. The first diode is a short, the second is an open circuit, the third one is a short. You solve voltages and currents and you check to see if it is true that this diode is open and that one is closed. And you report that, yeah, the configuration is true because, and you explain that, or it's false because. That is for the exam. Now, let's have some tutorial time with a circuit that has two voltage sources opposing one another. A smaller one, 5 volts, and a bigger one, 12 volts. They are opposing one another. Right now, as the circuit shows, yeah, the bigger one is winning. They're opposing one another, but 12 is greater than 5, and the current will flow counterclockwise through the external circuit. All right, so we will have current that will be flowing like this, right? The current is flowing like this through the external circuit, right? When that current arrives at the node on the top, it tries to go through D2, and that will only achieve opening D2. So D2 is now open, so that current has no recourse but taking the path through the right, and in doing so will close diode D1. When it reaches the node on the left, if it tries to pull downwards through D3, the only thing it will do is opening D3. So it will have nothing but turning right and closing through the 5, closing the 5, and continue to the right. On the right, it finds that D2 is already open, so it cannot go up. So it turns downwards and turns D4. It turns D4 on and continues and closes the circuit. So please observe that situation. That is when the source on the right is 12 volts. What happens if the source on the right somehow, miraculously, turns off and becomes a 0-volt source like this one? If that is so, the little source of 5 volts on the left will have its way and will succeed in pushing current clockwise through the external circuit like so. That current, when it hits that node, if it tries to go to the right, the only thing it will achieve is opening in D4, right? D4 is now open, and then that current has no recourse but to turn left and go through D3, and in doing so, will turn D3 on. When it reaches that node, if it tries to go up, it will just open D1, and then it has to turn to the right through D5, turning D5 on, and continues through the resistor. When it reaches the node on the right, it finds out that D4 is already off. That bridge is open, so it has to keep going up, and in doing so, turns D2 on and closes the circuit. D1, as we've seen that before, D1 is already off, so it closes the circuit like so. You say, this is interesting. So this time the current is flowing clockwise through the external circuit, but through the resistor the current is flowing from left to right. Please observe, the current is flowing counterclockwise through the outside circuit, but it's flowing from left to right through the 10 ohm resistor. Now it has inverted its polarity in the external circuit, but it's still flowing from left to right through the 10 ohm resistor. So you see those 4 diodes, D1, 2, 3, and 4, they are rectifying the alternate current in the external circuit. In the external circuit, we have an AC current that has one polarity half the time and the other polarity the other half of the time. But the direction of the current through the 10 ohm resistor is always from left to right. D1, D2, D3, and D4 are what we will name a full wave rectifying bridge, but that is for the future. Let's look that alternatively. You see, the current in the external circuit is alternate, but the current through the 10 ohm resistor is always flowing from left to right. It would be nice if we draw that circuit and we build it in the lab, but with diodes that show us whether they are conducting or not. And for that we will use the fireflies of diodes, the LEDs. These diodes, when they are conducting, they light up. And the more current that we pass through the diode, the brighter they shine. But if we exceed the specifications of the diode, they will burn. They go poof. How to identify in the laboratory the anode or cathode of an LED? Easy. The bubble, the plastic bubble on the top, has been shaved on the side of the cathode, and it has a flat side. That is a cathode. Or if you look at the pins, so the shorter pin is connected to the cathode of the LED. There, that is the way to recognize them. Well, this is what we will do in the laboratory. The details are explained in the lab. The 5-volt source is simulated with a voltage regulator connected to the power supply of 12 volts. Yeah, those are 5 volts. And then the voltage source that is alternating between 0 volts and 12 volts is simulated with a timer, 555 timer connected like so to 2 resistors and 1 capacitor. And the output of that timer, pin number 3, will alternate between 0 volts and 12 volts. That is the alternating source that we connect. And between them, of course, we connect the 5 diodes and the resistor like so. Half the time the current will flow like that. The other half the time it will flow like that, right? That is the same thing that we showed before. But because these are LEDs, when they turn on, they will bright. And we will see in the laboratory this is happening. This is a circuit that I want you to build in the lab. You have the regulator on the top, the timer in the center, the capacitor, the electrolytic capacitor connected to the timer on the bottom, and the 5 LEDs in the center, and the resistor is right in the middle there. Looking at that from the top gives you a perspective of how it is connected. And that is all, my invisible friends. I hope that you enjoyed this video as much as I enjoyed making it. I'm looking forward to meeting with you all in the second video of this series, the Ideal Diode. Until then, thank you very much and have a great night.